Good morning to everybody. This is the fourth webinar of Sunrise Project. Sunrise Project is a big consortium of universities and companies to develop a circular economy from a waste material. In particular, in this case, it is the polymer interlayer in laminated glasses. If you want more information about our European project, you can visit our website, in which you can find also the registration of all the previous webinars. This webinar will be about recycled materials for batteries. Indeed, batteries are a powerful tool to reach the energy transition and promote the sustainability of modern society. But for a real sustainability, we have to take into consideration the materials and the processes for the production, the use, and the disposal after use of these devices. For this, we have invited three speakers. The first speaker is Amideh Darjasi. She achieved her PhD in 2021, and now she is a junior assistant professor at the Department of Applied Science and Technology at the Polytechnic of Torino. She has carried out multidisciplinary research activities encompassing synthesis of active materials, chemical, morphological, and structural characterization, electrochemical analysis, and electrode preparation, with a particular focus to lithium-ion batteries, sodium-ion batteries, and supercapacitors. So, Amideh, please, the floor is yours.
Good morning, everyone. Many thanks for the introduction. Can you see my screen?
Yes.
It is my pleasure to share with all of you some of the results and insight we have been exploring in Sunrise Project in our group. Sunrise European project is aimed at recycling PVB. PVB, polyvinyl butyrol, is used as an interlayer polymer in the laminated glass, and which can be just considered just as waste. So Sunrise European project aimed at recycling this PVB, which then the high quality recycled PVB will be reused in the laminated glass, while the low quality recycled PVB will be repurposed in different applications such as batteries, carpet, and etc. We received some recycled PVB, which was provided by Luredera, our partner in Spain. They provided this recycled PVB by some mechanical process, and the molecular weight, the OH percentage, plasticizer of this recycled PVB in different categories were determined. So our aim, our goal as a partner in Sunrise is using this recycled PVB as a versatile material, serving as binder, separator, and finally a solid or gel polymer electrolyte. So in this presentation, I show some result regarding first PVB as binder, then separator, and finally solid polymer electrolyte. So first, using PVB as binder. While PVB has numerous advantages to be used as a binder, but it cannot be used independently in the electrode composition. So this report focuses on the mixture of PVB 20% of the PVB with other polymers like PAA and PVDF. So we used PAA PVB and PVDF PVB mixture as two polymer binder systems. So in this regard, for sodium-ion batteries, we made some laminates based on hard carbon, commercial hard carbon, 90%, 5% conductive carbon, and 5% binder. So the laminates was based on just PAA, the mixture of PAA, PVB, 80-20% ratio, PVDF, and then mixture of PVDF, PVB, 80-20%. So it is well known that hard carbon cannot be commercialized due to two problems. First is the poor rate performance and another poor initial Coulombic efficiency. As we can see, the performance of the laminate that we made, the PAA PVB mixture 80-20%, the green one, show the best performance in terms of the rate capability from low C rate to high C rate. Also show very high initial Coulombic efficiency of around 87%. That is very good. But however, in terms of PVDF, PVB, the mixture show worse the electrochemical performance, the black one, especially at high C rate. So we can consider an efficient two polymer binder system, PAE PVB 80-20%, that show very good rate performance, also very good initial Coulombic efficiency. The voltage profile of all the electrodes were shown, and we can see that in the sloping region we have adsorption, while in the plateaus we have interlayer insertion and pore filling process for all the electrodes. The cyclic voltammetry for PAA and then the mixture of PAA PVB is shown, that is in a good line with the voltage profile that we show in the previous slide. Regarding the initial irreversible performance process, the PAA PVB showed the less irreversible peak. So, which is in a good line with the better initial Coulombic efficiency of this electrode. Also, we evaluated the cycling performance open around 800 cycle, and this electrode show the capacity retention of around 79% with good, very high initial Coulombic efficiency of 87%, and open cycling, the Coulombic efficiency reached to 99.9%. That is very good results. I should mention that all of these we tried first with commercial PVB. Then I will show also with the recycled one. In order to analyze the SCI, the passivation layer of all electrodes, after cycling, we washed the electrodes and we made some XPS measurements, and we understood that the PAA PVB based electrode has a dense and thin SCI, while PVDF PVB based electrode has more thicker SCI. So that is why show worse electrochemical performance. All the measurements also was performed for hard carbon with all laminates for lithium-ion batteries, and as we can see, the PAA PVB based electrode 80-20%, the green one show the best performance from low C rate to high C rate, and also very good initial Coulombic efficiency, very high initial Coulombic efficiency of around 74%, but open cycling it reached to near 100%, 99.9%. Also, we tried to increase the amount of PVB to 50%, means PAA PVB 50-50%, but as you can see, the gray one, we lost a lot of capacity during the initial cycle. So it's not a good idea to increase the amount of the PVB to 50%. So again, an efficient two-polymer binder system is PAA PVB 80-20%. Also, we try to evaluate the long cycling performance of this electrode. And as we show at 1C, the cell show high specific capacity and very good initial Coulombic efficiency and capacity retention of around 81% upon 900 cycles. The interfacial properties of the electrodes also by impedance were evaluated that we understood that the PAA PVB based electrode has a more stable interfacial behavior. Okay, then we tried the characterization with recycled PVB that we obtained from Loureiro, our partner. As we show in the picture, it is the recycled PVB with some plasticizers, and we tried to make a laminate, again 90% hard carbon, 5% conductive carbon, and 5% binder with PAA and recycled PVB 80-20%. And as we show for lithium-ion batteries is the green, and sodium-ion batteries we show with blue. We can see that the both electrodes show very good specific capacity, high specific capacity, and good rate performance from low C rate to high C rate. However, we have some polarization during the initial cycle at low C rate that this can be due to the presence of some plasticizers. However, the results are promising for both sodium and lithium-ion batteries. And now the second part, we used also PVB as a membrane. So in this case, we mix the PVB with NMP. We add some isocyanate, very low amount, and then we let the solution stir to obtain a very uniform solution. Then we increase the temperature up to 70. And then the slurry, the solution casted on the glass with a Dr. blade, followed by immersion in the coagulation bath. And depending on the coagulation bath, we achieved two different morphology, porous and then separated. So we tried to do some characterization. Some of them are shown like uptake test, ionic conductivity, electrochemical stability windows that are very important for characterization of the separator. And we tried to compare the performance with CellGuard, that is commercial separator. And as we can see regarding the uptake test, the prepared membrane with PVB show even higher uptake test than CellGuard membrane. And regarding ionic conductivity that characterized by impedance, both porous and dense membrane show they are comparable, the ionic conductivity with CellGuard. And also electrochemical stability window that is very important for separator. We can see that the separator is stable up to 4.7 volts. We achieved also some, again, recycled PVB from the partner, Loureiro, and we tried to make the membrane and all the characterization again with recycled one. And we tried in a half cell for lithium-ion batteries with LFP as cathode and the lithium as anode. And as you can see, we could achieve the quiet, promising performance with recycled membrane. And at the end, I show the result regarding the PVB as solid polymer electrolyte. We use the solvent-free process that is a promising and good process to make the solid polymer electrolyte membrane. So in this case, we mixed PO PVB with lithium salt, and the ratio is PO lithium salt 15:1 and 21:1 with different percentage of PVB, 3 and 10% PVB. Then we mixed them without any solvent, we mixed all, and then followed by hot pressing at 80 degrees. Then in symmetric lithium cell, we made some impedance, and as shown for 21:1 PO lithium 21:1 and PO lithium 15:1, the PO lithium 15:1% with 10% PVB, the purple one, show the lowest bulk and interface resistance. So in terms of the impedance, we understood that 10% PVB with PO lithium 15:1 is the best percentage. It show the best promising performance. Also, we made in the symmetric lithium cell at 65 degree a stripping plating, and as we can see, again, the PO lithium 15:1 with 10% PVB showed the lowest overpotential value and also very stable behavior upon very long cycling. So as a conclusion, we tried to use PVB as binder, separator, and solid polymer electrolyte. So the result for binder, the mixture of PA PVB 80-20% is the best composition, is the best percentage that show it could enhance the rate performance, also initial Coulombic efficiency, that it was good for both lithium and sodium-ion batteries. And regarding the using PVB as a polymeric separator, we could successfully prepare for lithium-ion batteries the light and thin PVB dense membrane, which has a good uptake percentage, ionic conductivity, and very stable, electrochemically stable. And at the end, also, we made the PVB as solid polymer electrolyte to avoid to use liquid electrolyte due to problem of explosion and fire and etc. And we could understand that with the we can enhance the electrochemical performance by adjusting the salt concentration and also by changing the percentage of PVB. So for this work, I would like to thank to the group in Polytechnic of Turin and all of you for your kind attention.
Thank you very much, Abide, for nice presentation of the work. And now we can move to the second speaker of today, that is Dario Alvira from the University of Zaragoza. Dario, born in 1993, completed his PhD within the Aragon Institute for Engineering Research at the University of Zaragoza in Spain. His research focused on the development of carbon materials derived from various biomass residues and their modification for the production of high value-added carbons. He is currently serving as the project manager for the Marie Curie doctoral network Energy Zinc. That is a project entitled Towards Innovative and Affordable Sodium and Zinc-Based Electrochemical Energy Storage Systems composed of more sustainable and locally sourced materials. So, Dario, please, the floor is yours.
Thank you very much for the introduction. Can you see the presentation?
Yes.
Wait. No. Perfect. So I'm going to speak about agricultural waste as anode material for sodium-ion batteries. I want to give you a general introduction of this subject. So why we need to use agricultural waste is there's a huge production, around 5,000 million of tons per year in the world. And also there is a wide variety of residues or burning straws from the wheat straw, for example, or fruit wastes. So, what are the problems of this manipulation of these wastes? Is that, for example, the direct soil application can generate environmental problems such as CO2 emission or methane emission, contamination of water effluent, contamination of the soils, and also that the principal way to manipulate these residues is burn it in the soil. So also with this here, also with a lot of greenhouse gas emissions. So we need to use these biomass that are interesting raw material for what kind of applications. So starting from this biomass, these residues, we can perform different thermochemical, biological, or biochemical processes in order to produce direct energy, for example, through combustion or gasification fuels, as bio-oil, chemicals, as bioplastics, for example, fertilizers, and also carbon materials. And inside these kind of materials, there is biochar, that is the most used carbon material for now, to be used in soils to improve the agricultural growing of plants. The problem is that to produce these carbonaceous materials, we need to use kind of huge quantity of energy, so it's not very competitive economically. So it's better to find other alternative use, complementary use of this kind of carbons to increase the economic chain value of the carbons providing from the biomass. So we can activate or dope this kind of materials to be used in different applications, for example, as absorbents of gases, in the agronomy, as fuels, in the catalyst field, water treatment of to extract, for example, heavy metals or nutrients, and the subject we are speaking about, that is in the field of energy storage, to be used as active materials in batteries, supercapacitors, or also in microbial fuel cells. So regarding the energy context and why we need to develop new battery systems is that we have problems, as you know, with the global warming, the shortage of natural resources, and also we are increasing the energy demand. So we need to implement more renewable energy sources, and we need to store the energy we produce through intermittent renewable sources, as the wind or the sun, to be used when we need it. And between other kind of storage systems, there is the possibility to implement grid-scale battery storage systems. And for now, as also you know, the main batteries are the lithium-ion ones, but they have some issues as limited resources, not only for the lithium, also for other key materials as cobalt or natural graphite. So it's mandatory to develop new energy storage systems if we want to implement this kind of grid-scale battery storage for intermittent renewable sources. So between other alternatives, the most studied and the most promising ones, as Hamid said before, are sodium-ion batteries. And between other challenges, one of the main bottlenecks to apply this kind of technology is the development of high-performance hard carbon anodes. And for that, we need to design rationally this kind of carbons, taking into account the different sodium ion storage mechanisms. it's known that sodium can be stored in the hard carbon through 3 different mechanisms: intercalation between the graphitic or pseudo-graphitic domains, absorbed in the functional groups and defects in the surface, on the surface of the carbon, and also fitting inside the porosity of the hard carbon. So taking it into account, for now, there are different studies in the literature. Here there is a summary of that using different carbonization temperatures. So making pyrolysis to the biomass to produce hard carbons. As you can see, depending on the biomass you choose and the temperature you select, there are different reversible capacities of the active material. So we need to optimize it for each kind of biomass. But also we can turn the hard carbon properties to improve the performance in batteries. For example, performing some activation with chemical agents, or also doping the hard carbon with heteroatoms or also some metals in order to improve the conductivity of the hard carbon, and also to provide more active sites in which the sodium ions can be stored during the cycling of the battery. And I want to emphasize another kind of carbonization method to produce hard carbons, that is the hydrothermal carbonization of the biomass. For now, it was mainly studied for to produce hard carbon from synthetic organic precursors, but we think that there is a great potential to be used with biomass wastes or agronomical wastes. So this process consists on the carbonization of the biomass in a closed recipient with water, mainly water, at low temperatures and in autogenous pressures. So inside, several reactions take place, as hydrolysis, dehydration, decarboxylation, polymerization reactions. And that gave rise to different morphologies in the carbon, as the appearing of carbon nanospheres, and also the development of porosity. Also, this process allows us to include other substances to dope the hard carbon, for example, metals. And then it's compulsory to perform another pyrolysis step and an annealing step at higher temperatures in order to provide enough electronic conductivity to the material to be used in the batteries. So only to name some studies we have performed recently. We have studied how we can produce hard carbon from vine shoots, that is a residue from the wine production, but using pig manure instead of water in the hydrothermal reactor, in order to include, to recycle this residue, of course, that has several huge impacts in the environment, but also to introduce in the hard carbon some heteroatoms as nitrogen, phosphorus, and sulfur. So after performing these kind of experiments, we obtain hard carbon with interesting morphologies, and also, as I said, with high quantities of nitrogen, phosphorus, and sulfur that should improve the performance when it's used as anodes in sodium-ion batteries. And you can see here when we checked with this performance in hard cells with different electrolyte, we obtain a relative high rate performance for this material, much higher than for that hard carbons we produce only with the use of water. The next step we performed was to add some acids in the water solution in order to promote several reactions, mainly the hydrolysis of the biomass, and also to dope the material with sulfur, nitrogen, and phosphorus. And with that different hydrothermal carbonization, we obtained different morphologies in the hard carbons with, for example, more nanospheres or more 2D regions, more ordered ones or less ordered ones. And also in the inclusion of heteroatoms and the development of mesoporosity mainly. So when we check this material in sodium-ion batteries, we obtain it higher rate capabilities that I showed before. So demonstrating that this kind of hydrothermal carbonization with acid catalysis is positive for sorry, for the production of hard carbon for sodium-ion batteries. And the last one I want to show you is that we can also add through this process some metallic nanoparticles on the hard carbon surface. In this case, we added this molybdenum disulfide particles on the hard carbon surface through performing a direct hydrothermal carbonization of the biomass with water, but also with thiourea and sodium molybdate, in order to introduce these particles in the surface, since they can generate redox reaction and also intercalation with the sodium ions in order to improve the battery performance. As you can see here in the surface of the carbon, this kind of spheres made of molybdenum disulfide appear. And when we check the capacity, and there were also improvement comparing with other kind of synthesis, for example, only with water or like pyrolysis. So after showing these possibilities, I want to conclude giving an overall situation of this hard carbon productions. There is still a lot of work to do because each plant-derived biomass gives rise to completely different materials. So selecting the proper ones is a huge challenge, but also selecting what kind of thermochemical process we want to use, for example, hydrothermal carbonization and pyrolysis, and also all the pre and post treatment we can use as temperature processes, activation doping, and others I have not mentioned here because of we don't have time to go inside. And also that we need to take into account that the hard carbon, the anode material is only a part of the battery, so we need to study very well the interaction between the different parts of the battery, electrolyte separator, as Amida said before, also the cathode. So it's necessary to perform rational design of all the materials together in order to achieve high quality sodium ion batteries in the near future. So that's all. Here there are our contacts. Mine are from my boss. And if you want to know something more, you can ask when you want. And of course, if you want to collaborate in this subject, you are invited to do it. So thank you very much.
Thank you, Dario, for very nice presentation. And so now we can move to the last speaker of today. She is Eliana Quartarone from University of Pavia. She is full professor of physical chemistry at the Department of Chemistry at the University of Pavia. Her research field is focused on the design of innovative materials for lithium and post-lithium batteries. She is a leader of Archubat Lab, whose activities are focused on the development of novel and sustainable approaches for batteries recycling and reuse. She is the Batteries Europe Secretariat and Technical Advisor for the Battery for Europe working group about raw materials and of the Task Force on Sustainability. She is also coordinator of the Horizon Europe Renovate project, which develops new circular and chemistry-neutral approaches for recycling and recovery of battery waste feeds. She is author of more than 145 articles and 5 book chapters. So Eliana, please, the floor is yours.
Thank you, Alessandro. First of all, thank you also to the all guys from the Sunrise Project for the kind invitation and for giving me the opportunity to introduce the Renovate project, which has been recently funded by in the Horizon Europe framework. Can you see my screen, first of all?
Yes.
Okay. Thank you. Sorry. Fine. Renovate is, as already Alessandro mentioned, a project which focus to develop a new circular and chemistry neutral approach for the recycling and recovery of battery waste feeds. And is a low TRL project because the NTRL is 4. So for these reasons is a project that is under the umbrella of Battery 2030. Okay. Renovate is will be implemented thanks to the expertise coming from 11 partners, and is coordinated, for example, one national university consortium, Italian National University Consortium, INSTM, that is the coordinator of the project. Then also the consortium is joined by some university partners which will be involved in the development of recycling technology, innovative recycling technology. We also have on board 2 research centers, KIT and the Iberian Center for Research in Energy Storage, which are involved in sustainability assessment and also in the scaling up of some process we are going to propose. 2 large chemical companies, Syensqo and Organic Chemia, 2 small medium enterprise, Lomartov and Balance Technology Consulting, which are involved in the safety assessment and also digitalization, development of digitalization tools, a producer responsibility organization, the Italian ERP. But we have also on board 2 important partners, which are, as we can say, also the base of the project, because they are 2 batteries manufacturers, Fama, that is an Italian batteries producer, and also Svolz. The project started in January 2024 as a 3 years long project and has been funded by 5 million euros. The main goal of Renovate is the design and the development and the demonstration at low TRL of innovative and sustainable recycling technology that we are going to validate at lab scale. So it's a low TRL 4, more or less, for the European battery value chain, by recycling and reusing more than 95% of end-of-life batteries, but also batteries component in terms of, for example, metallic foil for the current collector and graphite, but also industrial side streams, which means, for example, the waste chemicals and solvents coming from the recycling process we are developing, but also, and most importantly, the manufacturing scraps that today represent the bigger part that the recycling plants are going to manage. This will be, the goal will be addressed by means of a closed loop recycling process approach for lithium-ion batteries, based on easily implementable net zero carbon process, which will address 2 kinds of chemistries, low value and high value chemistry, which means LFP-based technology and also NMC or LNMO chemistry. The first one, the LFP chemistry, will be managed by means of direct recycling, which currently is the best promising approach for the recovery of what we are now calling low values chemistry, if it's not so properly the proper name. And also by means greener and sustainable metallurgical approach for what concern the NMC-based chemistry, which are of course embedding the well-known critical raw elements like nickel, cobalt, and manganese. And regarding the NMC-based chemistry, such greener and sustainable metallurgical approach will be designed with a view, having a look at holistic and flexible strategies in order to make such technology easily adaptable for other chemistry, like, for example, the sodium-ion batteries that you mentioned before, which are usually embedding the same critical raw materials, especially nickel and manganese. Another important ambition of Renovate is also the smart reintegration of the side streams in order to have an almost net zero waste approach by minimizing the use of waste in terms of, for example, chemical and solvents that should be reused somehow, but also scraps, the manufacturing scraps, as I said before. The main ambition of Renovate is to address circularity in order to maximize the profitability of the recycling process we are going to propose and to develop. This means to think about innovation in the recycling that we know is a more or less an established stage, but we are thinking about a long-term research, so something new that we can bring in this field. Without losing the focus regarding the legislation and what the regulatory framework are asking in terms of targets. But this somehow supported by a digital monitoring and control, so we are going to contribute to create and develop a new digital architecture in order to have a clear and transparent digital platform, and least but not last, the sustainability and safety assessment by means life cycle assessments in order to feed the database in terms of recycling information, for example, regarding the carbon footprint declaration, that is one of the most hot topic that also JRC is taking into account. So we have on board partners which are involved in the digitalization aspect and also in the sustainability assessment. The main motivation of Renovate is to try to contribute to establish a resilient supply chain to boost European strategic action in these regards that is really important and crucial for Europe because, as you know, we are heavily dependent from third countries for what concern the supply of the basic materials necessary for the battery manufacturers. And that's why the European Commission is putting a lot of public money on this kind of project with recycling its fields, for example, not only the BEPA, the battery partnership, but also other platform in European platform like the European Raw Materials Alliance and also the interregional innovation investments. So there are a lot of funding tools, not only for innovation action, so for higher TRL project, but also for long-term research, because recycling is really important. And it's important for, especially for one aspect, as you know, because it's a physiological enabler of circular economy, because the production of secondary raw materials that you can have by recycling batteries is more convenient, not only from maybe not so heavily from an economic point of view, but for sure from an environmental point of view, because to produce secondary materials has a low carbon footprint impact with respect to the mining and extraction of primary materials. Another important aspect in recycling that in principle the materials can be recycled and reused infinite times. Of course, recycling cannot replace virgin materials in order to sustain the battery production in Europe, but of course this is an important strategies in order to secure the supply chain by keeping in Europe the black mass that is a really big tracer, because it's a potential source of raw materials for not only electric vehicles, because we are strongly focused on the electric vehicles, but we should also take into consideration that we have a lot of batteries also in the storage application. So, of course, you know that this is a quite known picture that we have maybe we will face in the next future a lot of batteries that will go to end of life, or, for example, to repurpose or reuse. Because there are more or less 1 terawatt-hour of announced production capacity by 2028. This is a quite tunable data number, because maybe more or less half of such capacity will be really set in place. But this is information that, if the Green Deal will be addressed, we will have a lot of batteries that will be produced in Europe, and this means to try to secure such supply chain as mentioned before. And of course, the number of gigafactory announced in Europe will recall for a high investment in the recycling field, with an expected also high revenue in terms of economic point of view, especially if a closed loop recycling will be unlocked, which it's really crucial in terms of circular economy. Why? Because a closed loop substantially means to recover, to extract the critical raw materials from the batteries during the recycling process, and recover them and using them as secondary materials in the production of new batteries. This, of course, will bring a positive impact in the European ecosystem, somehow buffering our dependence on primary battery material sourcing. We are more or less ready for what concerns the portable batteries, because we are approaching, and now we are slowly approaching the EV batteries in a longer time, with, of course, positive impact for what concerns the product lifetime carbon emission by over 30%. This is quite clear in Europe, and in fact, the battery regulation, the updated battery regulation, is asking us for a mandatory use of recycling content in the production of new batteries starting by 2030 or 2031. So recycling is one of the basic pillars for making more sustainable batteries. So it's really is occupying a really important place in the battery regulation. However, battery regulation is asking also for really challenging targets, especially in terms of recovery targets for specific materials. And even if recycling is already at an established stage, there is a lot of improvement, plenty of rooms for improvement that science and technology can address. So there is the need to a lot of new research in order to basically improve the profitability of recycling, for example, working on the chemistry adaptability in order to improve all the pretreatment steps in terms of safety. So, for example, a safer the activation, the automation, and the robotics in disassembly of the batteries. Of course, to try to implement digitalization also in the recycling steps, to have a look at the net zero waste in such technologies, and the implemented life cycle assessment that still lacks some data, especially in the cradle-to-cradle approach, and of course the design for recycling. So looking at new materials that can be easily recyclable in the early stage of the battery design and manufacturing. You already mentioned something in the previous interesting talks about new materials that can be used in order to make the batteries easily recyclable. So taking into account such aspect, it's important to have long-term research, and Renovate has some key innovation and some key ambition aspect in such 3 years of the project life. The first key innovation we are going to propose is to implement and develop new and innovative separation technology. So to prefer, in order to go towards a better disassembly instead of shredding process. This because it's important to try to have more value within the circular lithium-ion battery supply chain with simplified downstream. So the improved separation will allow to have higher quality materials by reducing also the purification steps. This kind of technology is the high voltage fragmentation that will be implemented by our partner, the Polytechnic University of Milan. And this technology will allow the separation of the conductive metallic foils and separators and other plastic from the active materials, not cathode, both cathode and anodic, in order to have high quality black mass that then can be further managed and treated in order to have the recovery of such materials. And especially high voltage fragmentation is really well fitting the direct recycling because for the reason I mentioned it before, and it is also a technology that can be easily customized on demand, depending on the type of chemistry. Another important aspect we are, from innovation point of view, we are going to implement is the use, the recovery also of non-active materials, non-electronic components. So it's important to us also, in order to enhance the recycling profitability, to recover graphite, for example, but also binder and electrolytes. This because such components are really important from an economic point of view, but also if you think, for example, to graphite, if graphite is burned out, there is a negative impact on the carbon footprint, and also binder, especially the polyvinyl fluoride, is a fluoropolymer that is not properly managed during the recycling stage, can cause the emission of hazardous product, like, for example, PFAS. So we are going to recover them just for an environmental but also economic point of view by a sustainable technique, like, for example, flotation in case of graphite, and supercritical fluid extraction in terms of binders, but also electrolytes, because in this case we have also the possibility to recover the waste solvents and that can be reused for other applications, for example, in case of CO2 as precipitated agent. The last innovation point that I want to put the attention, because it's the core of the process, is the implementation of direct recycling. Direct recycling means to recover, and by regeneration and healing strategies, especially the cathode active materials, for example, in case of in order to avoid the metallurgic approach, which consists of several steps, which are, of course, have an impact from an economical, environmental point of view. So we can directly heal the cathode by adjusting the regeneration, the morphology of, for example, the lithium stoichiometry, because we have physiological lithium loss. And this is really fitting the LFP-based chemistry, which are now considered low-value chemistry. So it's really hard to justify a hydrometallurgic approach or also pyrometallurgic approach when we want to recover just lithium iron phosphate. The recovery of the recycling of LFP is really, really important now, because there is a even grown demand for this kind of chemistry, even in the electric mobility. So a substantial capacity dedicated to the LFP recycling is really growing soon, especially in China and South Korea. There will be 48 companies by 2026. That is a really huge number, if even higher than the availability of manufacturing scraps than can be recycled today. And the goal is to recover lithium and phosphor, I mean carbonate and phosphate, but also start to work to the scaling up of the direct recycling that is now just working only at lower technology maturity. Just to skip, because the time in really running fast, we are happy also to work on a project which is really well integrated in a sort of cluster with other recycling projects, like, for example, with higher TRL, in order to accelerate the scale up of the outcomes coming from the Renovate, because we are, of course, coordinating the Renovate, which a low TRL project, because the end value is 4. When we are going to develop, as mentioned before, emerging technology, especially the direct recycling of LFP, but also the recovery of other components. But such results can be also somehow integrated in another project where we are partner, Automat, which is a higher TRL7, which is focused on the development of advanced disassembly, deactivation and discharging and sorting solutions supported by digital decision systems. And finally, also a sort of validation of our process in what is BATMAS, that is an Interreg, is a large project funded by i3 Tools, which is the first project which will implement the first European circular battery valley, with the deployment of breakthrough green technologies, around 4 demo lighthouse with very big partners like, for example, Orano Mining, Verkor, and so on. So it's also important just to say that activity like this one, clustering activity from the dissemination point of view, but also the technical exchange of knowledge is really important in order to accelerate the scale up of the recycling of new, innovative, and more sustainable recycling technology. So I think this was my just last slide in order to take too much time. So I kindly invite you to join us our journey, and I thank you again for your kind attention, and I thank also again the stream teams and the friends for having me today. Thank you again.
Thank you very much, Professor Quartarone, for this very inspiring presentation, and thanks to all the speakers for giving us this very nice overview of the topic, from lab scale to the whole European scenario. I just would like to share briefly the screen to for an advertisement for the next webinar, that the last one in agenda for Sunrise project, that will be held in 1 or 2 months. That will be about the life cycle assessment, so something that was already discussed a little bit in the presentation of today, and there will be our partner that will explain us how properly to carry out this wall assessment, with a specific reference to the case study of polyvinyl butyrate. I still invite you to visit the Sunrise project website to check all the news about the project, and to see also the previous webinars. And thank you all for the kind attention. Now I will interrupt the registration.